When we picture an ostrich or an emu, we see magnificent creatures perfectly adapted to life on land, yet unable to fly. Their long, powerful legs allow them to run at impressive speeds, and their large bodies are built for endurance rather than flight. These birds have evolved to thrive in open plains and grasslands, where running is more important than taking to the skies. These birds, along with cassowaries, rheas, and kiwis, share this remarkable flightless trait. Each species has adapted to its unique environment, from the dense rainforests of the cassowary to the open plains of the rhea, and the shadowy forests where the kiwi forages at night. Despite their differences, they are united by their inability to fly, a trait that has fascinated scientists for generations. For a long time, it was believed these birds descended from ancient ancestors that never flew. Fossil evidence seemed to support this idea, showing large, flightless birds roaming prehistoric landscapes. The story appeared simple. Their ancestors were always earthbound, evolving to fill ecological niches where flight was unnecessary. However, genetic studies revealed a surprising twist. Flying tinamous, small and often overlooked birds native to South America, are closely related to these giant flightless species. This unexpected connection suggested that the story of flightlessness was far more complex than previously thought. This discovery challenged the long-held idea of a purely flightless ancestry. Scientists began to question how and why these birds lost the ability to fly, and what this meant for their evolutionary history. The evidence pointed to multiple independent losses of flight, rather than a single event. Genetic analysis also showed that these birds diverged after the continents had already separated, debunking the old continental drift theory that suggested their ancestors were simply stranded as the landmasses broke apart. Instead, their evolutionary paths were shaped by more recent and dynamic events. The truth was more dynamic. Their ancestors were capable flyers, able to cross vast distances and adapt to new environments. Over time, as they settled into habitats where flight was no longer necessary for survival, they gradually lost this ability, evolving into the remarkable flightless birds we see today. This revelation has completely reshaped our understanding of their evolution, showing us that nature's story is often more intricate and surprising than we ever imagined. For decades, scientists puzzled over the origins of flightless birds and their mysterious spread across the globe. The evolutionary puzzle was finally unlocked by a remarkable fossil discovery: Lithornis promiscuus, an ancient bird that lived over 50 million years ago. This fossil included a nearly complete sternum, the central chest bone that anchors powerful flight muscles, crucial for the mechanics of flight. Using advanced techniques like geometric morphometrics, researchers compared the shape and structure of Lithornis's sternum with those of modern birds, both flying and flightless. The results were astonishing. Lithornis's sternum closely resembled those of today's long-distance flyers, such as herons and cranes, rather than the flat, reduced sternums of flightless birds. This provided clear, compelling evidence that the ancestors of modern flightless birds were once capable of epic journeys, traversing vast distances and even entire continents. The discovery confirmed that the ancestor of today's ostriches, emus, and other flightless birds was, in fact, a strong and capable flyer. Lithornis had the power to fly across oceans and continents, explaining how their descendants ended up scattered across the world, from Africa to Australia and South America. These ancient birds didn't simply drift on moving continents, they actively flew, seeking out new habitats and opportunities in distant lands. This groundbreaking finding rewrote the evolutionary story of paleognaths, highlighting the remarkable flying prowess of their ancestors and challenging long-held assumptions. The mystery of their global distribution was finally solved, not by continental drift, but by the extraordinary abilities of their flying ancestors, forever changing our understanding of bird evolution. Knowing their ancestors could fly, a new history emerged. Flight was lost multiple times, independently, across different continents. This parallel evolution shows the journey to flightlessness was repeated globally. Each group settled in new lands, eventually giving up the sky. The tinamou, a weak flyer, links to the past, showing flight was the default state. Once in new lands, evolutionary pressures shaped their destiny towards a grounded life. Abandoning flight can be a sensible strategy. Flying is energy-intensive, limiting size and weight. In predator-free environments, natural selection favors losing this costly ability. After the dinosaurs, few large predators existed, reducing the need for flight. Birds grew larger, trading flight for size and strength. Over time, they adapted to new challenges, evolving new defense mechanisms. The ostrich, for example, developed incredible speed and a powerful kick. These adaptations allowed them to thrive in changing environments. The story of flightless birds is a fascinating example of evolution's remarkable adaptability and creativity. Across continents, birds like ostriches and emus have lost the ability to fly, yet have thrived in their unique environments. Their powerful legs and keen senses are a testament to how evolution shapes species to fit their surroundings. The dodo, a famous flightless bird from the island of Mauritius, followed a similar evolutionary path. Isolated on a remote island with no natural predators, the dodo evolved to become large and ground-dwelling. But this specialization made it vulnerable to change. The dodo's ancestors were once flying pigeons, but over generations, they gradually lost their ability to fly in the safety of their predator-free home. This adaptation allowed them to thrive for centuries, but it also left them unprepared for new dangers. When humans arrived on Mauritius, they brought unfamiliar animals and hunted the dodo, introducing threats the bird had never faced before. The dodo's inability to escape or adapt quickly enough led to its tragic extinction. The fate of the dodo serves as a powerful warning about the vulnerability of specialized species to sudden environmental changes, especially those caused by humans. In contrast, ostriches and emus faced evolving predators over time, allowing them to adapt gradually. Their speed, size, and social behaviors helped them survive in challenging landscapes. Their evolutionary journey reminds us that traits like flight are not permanent, but are tools shaped by the needs of each era and environment. By studying fossils and genetics, scientists continue to uncover these incredible evolutionary stories, revealing how life adapts, survives, and sometimes disappears forever.